So once we understand this concept of the null space of a matrix, we can then proceed to define what's called the eigenspace of a matrix corresponding to a certain eigenvalue. So remember, we say that a scalar lambda is an eigenvalue if the associated characteristic matrix is singular. Well, let's say that we're working with an eigenvalue lambda. The eigenspace of our matrix associated to that eigenvalue is notated with this fancy E sub A of lambda. And what this is referring to is not the null space of the original matrix. It's the null space of the associated characteristic matrix. So the eigenspace of A associated to the eigenvalue lambda is the null space of lambda times the identity minus A. And this might seem like an awkward definition, but something amazing pops out of this definition. Every vector v that lives in this eigenspace satisfies what equation? So ask yourself, what equation would this vector satisfy? Well, we're looking at the null space of A matrix, not the null space of A, but the null space of lambda times the identity minus A. So if we say that this vector lives in that null space, what we mean is that if we take this entire matrix and multiply by v, we should produce the zero vector. So that's this equation. If we're working with a vector in this eigenspace, we know that lambda times the identity minus A, that whole matrix, when we multiply by v, we get the zero vector. And now what I want to do is I want to play with this equation. I'm going to distribute v in this equation. So the first thing I'm going to do is distribute v to the identity matrix, and then we distribute v to A. Well, when we distribute v like this, the identity matrix times v is just equal to v, and A times v is just AV. So this expression, when we distribute, ends up looking like this. Lambda times v minus A times v equals the zero vector. And now I'm going to play with this equation a little more. I'm going to move lambda times v to the right-hand side of this equation. So of course, lambda times v, I need to subtract it off from the zero vector, which just gives me negative lambda times v. So now my equation is negative A times v equals negative lambda times v. And of course, those negatives cancel. So what we're saying is that the vectors in the eigenspace are defined by the equation A times v equals lambda times v. This is an extremely important equation, and this is what it means for a vector to be an eigenvector. So the vectors that live in the eigenspace of A associated to an eigenvalue lambda must satisfy the equation A times v equals lambda times v, and we call these vectors eigenvectors. This is ultimately why we care about eigenvalues. We care about eigenvalues because eigenvalues lead to the concept of eigenvectors. So let's see an example. So if you're looking for eigenvectors, what you're looking for are vectors that satisfy the equation A times v equals lambda times v. So here we're looking at an example where we have a 3 by 3 matrix A, and on the left here we're multiplying by a vector v whose coordinates are negative 3, negative 2, 1. And when we do this matrix vector product, we produce the vector 6, 4, negative 2. Well, one thing to notice is that 6, 4, negative 2 is negative 2 times the vector v. So this is actually communicating the equation A times v equals negative 2 times v. That's telling us that v is an eigenvector of A, and the associated eigenvalue is negative 2. On the right over here, we're taking our matrix A, and we're multiplying by this vector w, whose coordinates are negative 4, negative 4, 5. And when we do that matrix vector product, we produce the vector 5, 3, negative 1. Now, if we look at this close enough, we see that 5, 3, negative 1 is definitely not a scalar multiple of negative 4, negative 4, 5. I mean, if it were, we would have the third coordinate would have to be scaled by a number that takes 5 to negative 1. So the appropriate scalar would be negative 1/5. But if I multiply negative 4 by negative 1/5, I certainly do not produce 5. So here we see that A times W is certainly not a scalar multiple of, that's a typo here, this should say W, not V. So I'll make a note of that. I'll fix that in the slides. So the key thing here is that A times W is not a scalar multiple of W. So what's the conclusion in this example? These two equations are telling us, on one hand, that this vector V is an eigenvector of A, and the associated eigenvalue is -2. The way to communicate that mathematically is to say that V is in the eigenspace of A, where the eigenvalue is -2. And of course, W here is not an eigenvalue of A. Or sorry, is not an eigenvector of A. Here we have another example. So here we're given the data of a matrix. So this is a 3 by 3 matrix. And someone is telling us that the eigenvalues of this matrix are -5 and 2. Well, for lambda equals -5, remember that the eigenvectors live in the associated eigenspace. So that's E sub A of -5. And by definition, this is the null space of -5 times the identity minus A. Well, how could we describe every vector in this null space? So how could we describe every eigenvector associated to -5 as an eigenvalue? Well, we look at the characteristic matrix. That's -5 times the identity minus A. And if we want to solve the equation, that characteristic matrix times x equals the 0 vector. So to do this, we row reduce that characteristic matrix, and we get this reduced row echelon form here. We see here that we get one free variable in that system, and if we play around with the equations, what we find is that every vector in that null space is a scalar multiple of -1, -2, 1. So the way I view this is, the way I would think of this is I would say that every eigenvector of A associated to lambda equals -5 is a scalar multiple of -1, -2, 1. What about the other eigenvalue? The other eigenvalue is lambda equals 2. If I wanted to find all of the associated eigenvectors, I would look at the eigenspace, E sub A of 2. By definition, that's the null space of the characteristic matrix, 2 times the identity minus A. To actually look at that null space, I need to reduce the characteristic matrix. So here I have the 2 times the identity minus A. And I want to look at the null space, so I row reduce that matrix to get this reduced row echelon form. And here I find that I'll have two free variables in the system, characteristic matrix times x equals the 0 vector, which means that when I look for all solutions, I should have 2 degrees of freedom. And when I solve those equations, I got that all of those vectors are the linear combinations of 3, 1, 0 and 4, 0, 1. So the way I think of this is that all eigenvectors of A associated to lambda equals 2 are the linear combinations of 3, 1, 0 and 4, 0, 1. So this gives us a complete description of all eigenvectors of this particular matrix. Someone told us what the eigenvalues were, and once we had that information, we could find all eigenvectors by looking at the associated eigenspaces. For lambda equals -5, that eigenspace is defined as the null space of -5 times the identity minus A. And by row reducing, we can look at every vector in that null space. For lambda equals 2, the eigenspace is the null space of 2 times the identity minus A. And by row reducing that characteristic matrix, we systematically describe every vector in that null space, which gives us a description of all eigenvectors of A associated to lambda equals 2. The last thing I want to say about eigenvectors is to maybe put a geometric spin on this situation. If you think about the eigenvector equation, what it says is that A times V has to be lambda times V. What this is really saying is that A times V is a scalar multiple of V. And if you view V as the input of the process and A times V as the output of the process, what this equation is telling us is that the output in order to be a variable, an eigenvector must be parallel to the input. So let's look at like a visual example here. Here I have a 2 by 2 matrix A, which I can view as a machine that goes from R2 to R2. So if you give me an input vector into this process, I can multiply A by the input vector and produce the output. So if I hit A with the vector 2, 0, I produce the vector A times V equals 2, negative 2. If my input vector is 1, 1, I can hit 1, 1 with A, and I produce 3, 3. Now, what's cool about this example is I can look at those inputs, and I can look at the outputs. In this figure, I'm doing those separately, but all of these vectors live in R2, so I could superimpose these two pictures, and something kind of interesting happens. If I look at the vector V, that's plotted right here. That was the vector 2, 0. When I multiplied by A, I produced 2, negative 2, and that's plotted down here. Well, here I get a visual indicator that A times V is not parallel to V. I sorted that myself algebraically up top here, but by superimposing these images, I can just look at the input and the output and see that they're not parallel. That tells me that V is not an eigenvector of A. On the other hand, when I multiplied A times W, I got 3, 3, which of course is 3 times 1, 1. So that tells me A times W is 3 times W, which means W is an eigenvector of A, and the associated eigenvalue is 3. And I see that visually here because I've plotted the vector W, and then I've also plotted A times W, and we see here, right here that the output is parallel to the input. So this is sort of a visual way to confirm that W is an eigenvector of A where the eigenvalue is 3, while V was not an eigenvector of A, so there is no eigenvalue to discuss there. So of course the thing that allows us to do this is that our picture is in 2 dimensions. Of course, the theory extends to any number of dimensions, so it makes total sense to talk about the eigenvalues and eigenvectors of a 30 by 30 matrix. And when we work with those things, I try to make geometric analogies to these smaller examples.